So I'll have a video camera there. Also, it will be recorded in the Zoom. So it's, the idea that everything will be recorded, such that you will be able to see it once again afterwards. And I'll try to upload it to the YouTube and VK. Okay. All right, so I press record. Guys in the Zoom, can you hear me?
Yeah.
Great. So let me know if something is wrong. You can write in the chat or use your mic. All right, so our course is called Simulation of Robotic Systems. And the idea is that I'm going to give you the basics information about robotics in general. And simulation is the first tool that you're going to need. I mean, you cannot do anything without simulation. So the point of the course is to give you some knowledge in modeling and simulation. We'll talk about it. We'll try to understand what is the difference between simulation and modeling. So I will give you a very crash course on modeling. How can you derive differential equations? Why do you need it? Actually, do you need it or not? So we will gonna discuss it. Then we'll take a look at the modern simulators. And if previously I was talking about MATLAB because it used to be a great simulator a few years ago, and we have a license, but before the famous or infamous stuff that we we don't have any license right now. So, and more than that, open simulators like Mojoko, they are state-of-the-art simulators. They used in the many publications and many research, and I believe that even if history went with a different path, we still would use Mojoko. So Mojoko is Python based. Actually, you can use a C version, but I'm not an expert in C. So a little bit an expert in Python, just a little bit. And I will show you a little bit how to use it to do simulation. So finally, we'll have the full course on kinematics and dynamics and a little bit control. So this is the general agenda for this week. So it's a lot of information, and it's not like I know everything about this stuff. I started studying this stuff like in 2019. When Stefano Stromajoli came to us as a co-head of our laboratory, and he showed us, he showed me this world of modeling and stuff. And still, I'm working on getting deep in this knowledge. So, but I believe that I'm capable of giving you the core of this stuff, such that you will understand the intuition. So we're not going to go into the details, and since there will be a lot of stuff, do not try to understand everything. You need to catch the idea, and then with your own pace cover this material. And just for you to know, I spent several nights to remind myself this material. I haven't done everything that I wanted, so it's a lot of information, and I spent more than 5 years studying it. And it's just for you to understand that there's an iceberg, and I'll give you just a tip of iceberg, and this is up to you to study the rest of it during your professional career. It's like general idea for the course. And then, how are we gonna do this? I'll try to give this course in a different manner. such that I will try to avoid any presentations. So we'll try to make it as live as possible, and I'm going to use my iPad, and I'm going to make notes on the iPad, and it will be screened here, so it will also be recorded, and we will go from the PDF files with lecture notes up to notebook notes that I will gonna make by my hand, and then to the code and vice versa. So we'll try to do something like this. It will be the first time, but probably it will be easier and better for you. At least I wish that. Any questions so far? All right. So. It's a very difficult setup. So I have an iPad, I have an iPhone here, there, and my laptop here, and a bunch of notes for myself. So I'll try to go through all the material. So, so I'm gonna share screen. Sure. So. Guys on Zoom, can you see the screen?
Yes.
Nice.
Yeah, that's it.
Great. So now you have to see my iPad. So okay, no, it will be better to leave it like this. Okay, so I'm gonna write some stuff here. So we'll start with a title. So simulation of robotic systems. Let's start with the word simulation. What does it mean? What do you think?
Mathematical modeling of the processes that go.
Okay. What is the difference between modeling and simulation?
Modeling is describing the system using some equations or differential equations.
Mm-hmm.
But simulation is trying to get a result or response from these equations using some types of input.
Yeah, you're right, actually. That in Russian it's almost the same word, and this is why in Russian we have моделирование and имитационное моделирование, since in Russian it's the same word. We need extra word next to it. In English, it's different words. And modeling, it's the process when you create model. So model, it's something that represents your reality. For example, when you create a 3D model in CAD software and then you 3D print it, it's also modeling. So you have something as a your interest. So it's like an entity of interest. And what do? You create some kind of a representation. Representation of it. And this is modeling. And modeling, it could be, you can tackle different kind of models. So it could be statistical model, it could be 3D printed model, it could be CAD model. But here we are going to talk about equations. So equation, like something that represent the dynamics, you know. And when you talk about model and the process of modeling, you need to do the right model. I mean, I do not have any resistor here, but let's assume that it is a resistor. What kind of model should I use to model resistor? What kind of law should I use? Ohm's law, right? What kind will it help you to describe the motion of this resistor?
No.
You know, so also it has physical structure, and for this particular process I could use Newton law, right? And this is why you need not just model something, but to really understand what is the crucial thing here. Where should you make an emphasis? Could you find it? I'm probably going to use it once again. Not just to throw at you, but I would like to make a fun and clear statement that you need to understand what you're doing when you do derive the equation. Thanks. So you need to, so there's two stuff, verification and validation. Verification and validation. So first of all, you need to understand that your model is correct. I mean, the Ohm's law, the second Newton's law is correct, but it is not correct model to represent something that you are going to do, right? So maybe your model is correct, but it is not correct for your particular system. It's like semantic and syntaxis errors. So it's like the same stuff here. So you need to be careful with that. Okay, so let me write down. So modeling is an act of creation of a model. Great, but our course is called simulation, right? So what is the simulation then?
Testing this model.
Right. So I'm gonna work out this term test. So our task not just to test, but to study it. So we're gonna use models to study something that we would like to test. So we're gonna use models to test the entity. And our aim is to understand the behavior of it and performance. So the simulation is an act, of using this model, the model, to understand behavior and performance. Behavior and performance, right? But in order to do simulation, you need a model. In order to have a model, you need to derive it. So this is what we're going to make. So you need modeling to do simulation, right? Right? So without it, you won't have any simulation. What else? What else? Why do you what is the second reason you do modeling? Okay, we discussed simulation. What else? Why else you need modeling? Is it just only simulation or maybe something else?
3D printing, like for some parts, maybe mechanical.
Let's stick to the equation. So we already went through this 3D printing. So you have an equation. You can use this equation to do the simulation. What else?
Maybe we need to create something.
Create something. What do you mean?
Like in control theory, sometimes we model the system, then we use the equation to represent the controller. Then
Yes, you're right. So you use also to synthesize your controller. So in order to do control, you need modeling. So we will take a look at how models can be used for the simulation and for the control. So basically, the same equation can be used in order to make a model. For example, you can write down an equation to our pendulum. It's something that we're gonna make, and you can use it in order to simulate the robot passively, or you can use this model in order to make model-based control. So we need modeling for simulation and to do control. And this is the main line of the entire course. So we will study modeling as a part of the simulation process and for the control processes. Okay? Great. I need a pen. Okay, so this is the main idea of the course. Let me tell you a little bit about the course, the structure of it. So we're gonna have 7 lectures. 7 lectures. And I believe it will be 7 practice. You got 7 practice? Something like this. Plus 7 practices. So lectures will be about, so the first lecture, the one that we have, it's general information, and I will try to tell you about simulation of very simple dynamical system. We're going to talk about spring and damper system. So it will be spring and damper system, plus I'm going to talk a little bit about integration and discrete ODEs. So discrete ordinary differential equations. So any dynamical system described by what?
We have 8 practice.
8, great. Maybe there is a mistake there because I've seen that I have 7 lectures, 6 lectures. 6 lectures. Maybe there is a mistake that it's supposed to be a lecture instead of a practice. So I will put a star here, so it could be different. So integration. So we're gonna talk about this a little bit. So then, from the simplest model, spring damper system, we move to the planar case. We consider 2R planar. 2R means 2 rotational joint planar robot, and we gonna talk about control, different strategies. Then maybe it's gonna take 2 lectures here, so I will write down 1, 2, and 3. Let me just change it a little bit. So here it will be 2 Lagrangian dynamics, Lagrangian. And then we're gonna talk about control. So I will write it explicitly. 2R planar robot control. Yes. Then we're gonna talk about spatial motion. So 2R case is very simple, basic trigonometry, but we will catch all the ideas, and after that we talk about spatial, I mean 3D Euclidean motion, spatial motion. So we'll start with a configuration, then we will consider kinematics, then dynamics, yeah, and finally something about control, basic one. So this is the idea for the lectures. At least it is planned. Maybe we'll stop something like on kinematics. We will gonna work with our own pace. And the rest of the material then you will cover by yourself, or you can watch videos from the previous years. So the lecture material pretty much the same, but I would like to just give it in a different manner. And then practice. So practice. So practice is a little bit tricky, since we just move on from MATLAB to the Mojoko, and Yegor is a great, I mean, he's very experienced in Mojoko, and he opened it up right today for the first time. Oh, yesterday. So Yegor, who is responsible for practice, will study it with you. As for the practice, it will be like 7 to 8 lessons, and one part of it will be like workshops, when guys will give you some insights, some basic knowledge, how to work with the documentation, and some comments on the examples that you can find out at the GitHub. And the rest of it will be Q&A. Q&A, mainly not on the simulation part, but on your project part and practice part. So it's like theory based. And so Yegor have done it a lot at MATLAB, so he will do this for you. For the practice, you will have 4 practice tasks. So practice 1 will be about 1D systems, like mass spring damper, so very simple, and plus integration. So you're gonna try different kind of integrators. Practice 2, it will be Mojoko simulation, like some kind of passive structure. So we'll try to make some kind of simulation model. So there is XML, there is a Mojoko format file. So you need to do something, simulation-wise without control. Practice 3 will be like almost the same, but with control, that we will study. Practice 4 to be discussed. It's something a little bit more different. We're gonna discuss it with the guys, so it will be something like a little bit more elaborated Mojoko simulation. Maybe it's something with the extra library like a Pinocchio. So something else. And basically all of this, it's like small breaks for you to make a fundament, like a base for your knowledge in order to make a project. And the project, basically you need to make something fun. So you can model anything else, whatever you like. Just you need to verify the idea with Yegor. So the tasks, what the aims, what you gonna do, how can you do the simulation, what kind of experiment you would like to make, and etc. etc. So right now I will do something that I do not like. I will show you some slides from presentation, but from just previous year. Where is it? Lectures. Yeah. So it's a lecture from previous year, and just a few screenshots from the project that students have done. So they had done some simulation of a car, of a walking robot, of a how do you spell it? Delta robot, and etc. etc. So very different projects, and basically you can do the same. For the project, the idea is that you do by your own. Each practice task is done by your own, because it's about your knowledge, skills, and building blocks. Project can be made in a group. In a group up to 3 people. And the idea of the project that you already know something, right? So you already been through your bachelor's, you have some kind of background. So the idea is to use your background, use the background of your colleagues, and use something useful from the course to make something fun. I mean, here there is no any strict tasks. What you can do only if you are if you have troubles with your imagination, then we can discuss it. But the general idea is that when I'm reading some paper, I always want to verify it. I always want to do my own simulation in order just to understand what was written in the paper, or just to verify. Is it true? Or maybe it's just some kind of bullshit is written there, right? So my supervisor, Sergey Kolybin, he told me at my PhD that what is the difference between master student and the one who just defended PhD. When he's reading the paper, master student, he can understand what is written. And the PhD candidate, he understands what is not written. Because your paper is all about your success. Otherwise, you do not write paper. So, what was hidden? Where is the bullshit? So, this is why I like do simulation. For the practice, any questions? Yes.
Can I do a project with?
What?
Can I do a project with the guys from the Russian language?
Mm-hmm. Yes, you can.
Do we have a specific deadline?
Yes, we will make them. Right now, I'm not going to give you dates. Maybe during the week we'll figure this out. Great. So you had task to give answers. By the way, the guys in the Zoom, let me. Guys in the Zoom, you need to answer on the questions. Chat. Where is the chat? Here. Zoom guys, please use this form and please answer some questions about your background. So we are gonna, while guys are answering, I will make the extra comment. So education-wise, there is a concept. Let me make some color here. So, a concept which is called I-shaped education, or I-shaped experience, something like this. So the idea is that a person has in-depth knowledge in something specific. So it's like eye or vertical line. Another one is a horizontal line when a person has a broad knowledge. He's a generalist. He knows a lot, but just a little bit in all. So it's a different stuff. It's a generalist. So and it has broad knowledge. Right? And there is extra structure which is called T-shape. So it's the one that has the both, who has broad knowledge and has in-depth knowledge in something specific. So our course is about this stuff. So here, the horizontal line, it is the lecture material. Of simulation robotic system, and this vertical line, it is your project. And and the idea that you use your previous background such that the project is useful for you, it is interesting for you, it's fun for you. Okay? I didn't get it.
What about rectangular knowledge?
Rectangular. With a closed form, I don't know. I think maybe it's something with soft skills. I don't know. It's not. It's out of the scope of the course. Okay, so let's take a look at the results. Yeah, now we have 17 answers. So, and here, yes, I can make it a little bit bigger. The majority have experience in programming. The no. Control and math, great. Then programming and design, CAD design, mechanical design, 15% suck at all of this. Little bit machine learning.
Well, it's one person, or
yeah, one person. So most of but still you can see that most of you, the background is different. And my aim was to create something which will be useful for all of you. And this is why it has this kind of structure, the T-shape. And for the same reason, maybe it will be difficult also for all of you. So maybe you're very great at control, but you're not very good at mechanics. But we're gonna do simulation of mechanical systems, so it depends.
So for one guy who is good at all of this, I think it will be easy.
Which color?
Like the blue, like the default blue.
Hardware, no.
Oh no.
Have background. So it's so it's something like an extra structure.
No, I think like it's blue. It's two blue colors in the right column, but they don't match.
I'm good at all of this.
Oh, no one chose.
No one picked this.
Yeah, nobody choose it.
Oh,
Okay. So this was general information. Let's do some kind of modeling right now. So we will start with a mass spring system, like the simplest dynamical system. So it has like a mass. Let me make it beautiful. And it has a spring and it has a damper. And this structure is very popular, it's common. Because this spring damper idea lies everywhere. It's like PD control can be treated as a mass spring system. Contact interaction can be treated as a mass spring damper. Constraints can be treated as a mass spring damper. So it is a lot. It's pretty common structure, and this is why we will tackle this. Okay. Let's assume that we would like to make a model. So our goal is to make a model. How we are going to make it? And that is. Can you?
Laws of motion, like Newton laws.
Newton laws. If our task is to derive an equation of motion, what kind of method do we have?
We have the
Newton-Lagrange method. So we're gonna right now we are gonna derive an Lagrangian equation. Do you remember how it's spelled? So I have a piece of paper here. By the way, it's lecture notes, which is uploaded to the GitHub, and it's already there, and you can read it. Okay, but still, I'm gonna write it down. So, in general form, you have the following. What is L?
Generalized coordinate.
L is a Lagrangian. And X is what is it? It's the state, yes. But for this simple system, it will be like state, and for this kind of system, it will be position. X is generalized coordinate. Can you give a description? What does it mean, generalized coordinate?
There's no constraint between them, they are independent.
Yes, maybe something else. Any details?
Like in the end, whatever the coordinate system is, we will get
Like
the same
joint angles.
the same equations.
So basically, the idea of generalized coordinates, that is a minimal coordinates to represent the whole state. I mean, you can use a lot of different numbers to represent this state, but it is like the minimum which is sufficient as enough. This is the main idea. So here, let us make the Lagrangian. What will be the formula for the Lagrangian?
Is K minus V, difference between kinetic energy and potential energy, I guess.
Right. So you need to take kinetic energy minus potential energy. So let me use a different color. So this will be the kinetic, and this will be the potential. No. Actually, by the way, if you will sum them, you will get something which is called Hamiltonian. Okay, so now what will be the kinetic energy for this mass sprung damper?
Half mx square, half mx square, mv square, sorry, mx square.
Right, so and velocity here will be just x dot. By the way, in YouTube channel, for this equation formula, I have strange comments, and it's very haha moment that some kind of crazy guy have written that I got a wrong equation for the kinetic energy. His idea was that it's not 1/2 m times v in power of 2. The
X dot square, sorry, x dot x.
I'm sorry?
No.
So his point was that it's a wrong equation, that the correct equation will be mass times velocity in power of 2. And his argument was that if kinetic energy only a half of mass times velocity in power of 2, what will be the another half? So it's like a half. Where's the another half? So it's kind of fun. Okay, so what will be the potential energy? Yes, mjx. Right. Great. So it's very simple stuff, and we can compose it, and we'll have something like this: 1/2 mx power of 2 minus mjx. And now, in order to derive this stuff, we need to make a partial derivative. What it will be? Minus mg, right? And we need now a partial derivative to not in respect of position, but in respect of velocity. What it will be? Mx dot, right? And now finally the full time derivative of the previous one will be mx double dot. So now we can compose the left part, and the left part will be mx double dot minus mj, right? So it will be plus mj equals to q, right? What will be the q? Yeah, you're right. So q is external force. So friction, interaction, our control is everything for the q. because the left part, that one, yes, it's all about inherent forces inside, so it's something which is inside, and the right part is something which is external. What will be here the external force?
Gravity.
No, gravity we already had in the Lagrangian, in the potential energy. It's something which is inherent. It is inside. But we don't have force right here. I mean, in this system I haven't written here.
It's a spring force.
Right. We have done just a typical mistake. So let's go back here. The equation for the potential energy. Actually, it has something else.
Potential energy of the spring.
Yes, 102, right, kx, so the Hooke's law. It also has in power of 2, by the way. So this is the part, and let us fix the equations. So it will be here plus kx. So it will be not plus, minus. And plus kx equals q, right? So spring is like a battery for the potential energy. So body is a kind of battery that store kinetic energy. You know, when I threw the marker, it got kinetic energy. It has also potential energy because we in the potential field, right? But in the space without gravity, it has only the kinetic energy. But the spring has potential energy. So let's go back to the Q. What will be the Q here? Zero. Yes. It's zero for the system that has any source that sucks energy in the system. So for the conservative system, it's supposed to be zero, equal to zero. So if there is no any energy dissipation, it will be equal to zero. But here we have a damper. What damper is doing? So the damper actually dissipate energy. Actually, it's not dissipate because of the second thermodynamics rule. You cannot dissipate energy. You can irreversibly transfer it to heat, temperature rising. So because, you know, in, the amount of energy is constant. And here Q will be an external part that sucks energy, and here Q will be force of the damper. So what it will be? Bx dot, yes, you are correct. So it will be Q and minus because it sucks energy. It doesn't add. Minus B times x dot. And finally, our equation of motion will be mx double dot plus mj plus kx equals minus bx dot. Do you agree?
Can I ask a question?
What did you tell? Excuse me.
I'm from Zoom, so I I'm not from a control background, so please verify my understanding that so if this equation equals to 0, then this system is in a equilibrium, and that means we have some external force that kind of push the spring.
Yeah, if the equation equal to 0, it means that the system is conservative. For example, it not in the rest position because your Lagrangian doesn't equal to 0. For example, if you make a model of a just mass springs system,
Yes.
the Q equal to 0. So you have oscillation. You have an
so
oscillation
this
without
model will
energy
avoid
dissipation.
friction.
Once again?
For this simpler model with only the oscillating spring, we're ignoring friction. So
Yes.
there's no energy loss in
Yes.
oscillation.
Yes.
Okay.
Yes,
But
and it's
then
called
we
conservative
have a-
system. It's isolated. It's isolated from any other, you know.
External.
Yes, yes, and the friction it's something which is external. You doesn't have real system that doesn't have friction, but it is a model. You know, we take this point of the model. That model must be. You need to validate a model. So if you make something like a mass spring without any damper, even if if you will take a real mass and real spring, each real spring has viscosity as an inherent property, and because of that, it's gonna behave as a spring damper system. You know?
Okay. Yeah.
So
This added damper, so this is like the way we simulate, the way we model external forces.
right. So this is something that I draw. It's ideal structure that doesn't exist in reality. I mean, it is our model, and this is why we do model damper.
So if I push on the mass, is that also part of Q?
Right, yes, it will be here. So if I add force here, it will be here. And you can treat it as a control part. For example.
Okay, and like if my force completely cancels the effect of the damper, that would result in a situation where Q equals to 0.
Yes, you're completely right. For example, if you would like to make a system that oscillates in real life, you need to inject a little of energy just to compensate friction and damping.
Yeah, and then when I achieve that oscillation where like the Q and F cancels out, is that the equilibrium state of this model?
So you will come to this, yes,
Okay.
to this situation.
Thank you. Yeah. I understood it all.
You had a question.
Would you please repeat why you write minus V star?
Because it just works in opposite direction here.
Because it just works.
No. It works in opposite direction. So it doesn't add energy to the system. It sucks energy from the system.
And also, Lagrangian, after like kinematic and potential energy, shouldn't there be like minus 1/2 kx squared?
Minus half plus
So, like,
Do you talk about this stuff?
yeah, this, like, because below, like, when L equals like 1/2.
Yeah, sure. Right, right. Nice. Okay. So, what should I add here? A little bit about of control. So basically, it is differential equation, right? Second order differential equation. And how do we solve it?
I don't know what's called. I know how to solve it. Like the name of the
Okay, let's go step by step. So basically, what we do represent any system. So just a little bit of background. So we represent any mechanical system as equation x dot equal to some function x that depends on x and u. What will be the u? The x? X is a state. It is state, and x. It doesn't mean that x is a position. It's kind of. It can be any vector that we consider as a state. And for example, what we can write down there, that state, it is a vector of our position and velocity, for example. So here it will be q is a position and v is a velocity. What will be the u? It's your input control, input. And the x dot, it is the state time derivative. State time derivative. And this is the called ordinary differential equation. What just we got it here? Basically, the stuff that we just derive, it is the same stuff. Just we need to rewrite it in some way. Let's try do this. So x will be let me change just okay, I am gonna use different x's. So this is the state, and it is position. Okay, it's not very good, but still, because I have the same x's here. Let's pretend that it is different x's. Okay, so the state will be position and velocity, x dot. And the state time derivative will be x dot, x double dot. So we need to write something like the equation on the right side of this slide. So let us do this. So we need basically to do the following. So mx double dot equal to minus bx dot plus minus mj minus kx. From here we can say that x double dot equal to 1 over m, and we can make it a little bit more pleasant like this. And
do I have an extra m before the gravity, the G?
extra m, yes. Any mistake? Is something wrong?
Yeah, in the last equation.
It was minus. No, it's okay.
Yeah. Like we factor out the m.
But I haven't done it yet. I believe everything is correct. You see, I have brackets here.
Okay, okay.
What we're gonna have x double dot minus equal minus bx dot m minus j minus kx m, something like this. And we need to put it here. So x dot equal to we're gonna compose it as a matrix. It's still something ugly. And x dot, it will be just like velocity v. So something like this, we can make it, we can go through and make it a little bit less ugly, but the point is that we just derive a passive structure, and if we have, if we had a control part, it in this case it would look like something like this, state and just state plus some input Jacobian, what is called times control. So something that doesn't depend on control, and something that that depends on control. So basically any mechanical system will look like this. But for now, since we have a passive structure, we have the first term. All right, what can we do with that? So what have we done just right now? We have done modeling. We created a model. Now we can use it for control, or we can do this for the simulation. So let's start with something basic stuff. Have you used MATLAB before? Yes. So we're not going to use MATLAB, but I'll just make a little picture. So you're familiar with the Simulink. So and the Simulink is just something that allows you to compose these differential equations. So let's create a block diagram out of the equation that we just derived. So let's assume for some reason that you have value for the acceleration, x dot. What should you do in order to find out the velocity? Yeah, you need to make to use an integrator, and there is a block in MATLAB that integrates the system and spits out velocity. What should I do in order to get position? Yes. And inside it, you can give the initial position, and it will be like a deflection of your spring. And here will be position. What should I do in order to compute spring force?
We will have to give a spring constant.
Yeah, so here, this is the spring force actually. So you take your position and you multiply with a k, so like a gain. And here you have spring force. How can you compute the damping force? Right, so I will make it like this, B, and this is the damping. I'm not sure about spelling, damping force. What else should you have? So this is the damper. And so what I would like to do, let me make it explicit. So I will copy this and put it here. So mx double dot equal to minus bx dot minus kx minus mj. So what else should I write? Minus mj, which is just fixed. It's some kind of coefficient. And now I need to sum everything up.
It's better to use mj and multiply it with -1.
Mj, yes. So mj and everything here is multiplied with the -1. And then we need just to multiply with the 1 over m, and we have a closed system. And this is how, using just summator, gain, and integrator, you can create a structure according to equation. So we derived an equation by hands. We have got an equation, and then we can use, for example, Simulink just to create a diagram, block diagram, and then we can simulate it. So it's like MATLAB style. And it's something that we don't do anymore. What we do, we'll consider, I believe, after break.